Okay, I think it's all set. Hello, everybody. So we continue where we left it yesterday. And I was at the point of defining the power spectrum of the gravitational wave energy density. Okay, so yesterday I demonstrated how to define the energy momentum tensor for gravitational waves. And from the energy momentum tensor, we actually found this particular formula. This is the T00 component. 00 means that these are time derivatives. And Hij is the metric perturbation. And we then yesterday focused on the case of the Friedman universe. Okay, so now in this case, we perfectly know what is this Hij because it is the tensor part of the metric perturbation over a Friedman background. So everything here is known. I then told you something more about this average here. So the fact being, there are two reasons for this. The first reason is that it is not possible to define the gravitational wave energy momentum tensor without making this average. And this was all that we have seen in the first part of the lecture, in which the average was necessary to distinguish what is the background, the curved background spacetime, and the curved fluctuation, so the gravitational waves. And these two quantities were actually split by performing this particular average. And this was an average that could be considered either an average over a characteristic scale or over a characteristic frequency. And then in the second part of the lecture, I claimed that there is a given reason why signals from the early universe are in the form of stochastic backgrounds, which means that one only can access the statistical process, the statistical properties of the signal. And the reason is basically the fact that the signal comes because of causality, that the signal comes from the early universe, and because of causality, the characteristic scale of the source and therefore of the signal can be at best of the order of the Hubble scale back then. And so today we see excessive number of superposition of uncorrelated signals with a correlation scale which is much smaller than a typical detector resolution. And therefore, in the end, what we see is a stochastic signal. This then entails that we need to treat both the source of the gravitational wave and the gravitational wave signal itself as random variables. And this particular average in that context becomes an average over realizations, over the ensemble. However, I also made the point that in the universe, one can apply this ergodic theorem, which identifies ensemble averages with space averages. Okay, and this is due to the fact that indeed, because we have access today many different uncorrelated Hubble patches, then we can assume that each of the Hubble patch is a realization of our random field, and therefore that instead of that averaging over the volume is the same thing as averaging over realizations. Okay, so with all this, basically we understand that we can identify this kind of average with a volume average, and therefore it is the same as the one that we used to define the tensor, the gravitational wave energy momentum tensor. Okay, so with this fast summary, I hope that now everything in this equation is clear. And it is also clear the reason why we are interested in knowing what is the power spectrum of the gravitational wave energy density. Maybe another point that is worth reminding is that we also said that the gravitational wave signal is a Gaussian signal. One can assume it to be a Gaussian signal for in most cases. Okay, there can be exceptions, but for most sources because of the characteristic of the source, we can assume it to be Gaussian. And this is also related to the fact that we access today many different independent realizations of this signal. And therefore, for a Gaussian field, the second moment is what describes fully the statistics of the random variable. And the second moment is the two-point correlation function, and in Fourier space, the power spectrum. Okay. So now we were then, yesterday we defined the power spectrum of the gravitational wave amplitude. And today we look at the power spectrum of the gravitational wave energy density. Okay, so this is the formula of the gravitational wave energy density. Here we have just converted physical time into conformal time. And we want to say that this is the integral overall wave number of the power spectrum. Okay, so this is the total energy density. It is the integral of the power spectrum defined per logarithmic unit of frequency. Okay, this is just a definition and entails the fact that the integral is in dk over k. Okay, and then what we can do actually is that we can write this equation, which is analogous to the one that we wrote down for the gravitational wave amplitude. But here you see, so R and P are the polarization modes, plus and cross. I did a Fourier transform in space with respect to here, but there is this time derivative. Okay, so the right-hand side is pretty much as we did yesterday. Okay, there is this delta function, which is simply due to the fact that the field is homogeneous and isotropic. And here there is another sort of power spectrum, which is the power spectrum of the time derivative of the gravitational wave amplitude. And now the thing is, okay, this particular power spectrum, we access it today, typically with a measurement at a detector. And today, as we have seen, the gravitational waves, they are freely propagating, okay, because we assume that the source has already taken place in the past. So today they are freely propagating sub-Hubble modes, okay, because obviously, as what I said, the source and therefore the signal is correlated on scales that are comparable to the Hubble scale at the moment of generation, and therefore today these are very well sub-Hubble. Okay. So the solution for freely propagating sub-Hubble modes was plane waves redshifting with the expansion of the universe. This we also saw yesterday. And therefore, this time derivative squared simply makes out a factor k squared with respect to the power spectrum of the gravitational wave amplitude itself. Okay, so this particular relation is only true in the case of freely propagating sub-Hubble modes. And then you can do a simple calculation that maybe is in the exercises. Okay, so you can Fourier transform in space now this in K, I mean these two quantities, apply this formula. You will have here an integral over K, equate the integrand, and this is what you find. for the power spectrum of the gravitational wave energy density per logarithmic unit of frequency. Okay, it's basically k squared times the power spectrum of the amplitude that we defined yesterday. And I already told you yesterday that this particular quantity goes like 1 over a squared. And therefore, here we have twice 1 over a squared, and we obtain this very expected behavior that the gravitational wave energy density is redshifting like 1 over a to the fourth for freely propagating subbubble modes, so radiation mode. Okay, so gravitational energy scales like radiation for freely propagating subbubble modes because they are free massless particles, so a bunch of gravitons. Okay, and then what is also customary to do is to define the gravitational wave energy density parameter. Okay, which means that you normalize the gravitational wave energy density with the critical energy density of the universe today. And this quantity, before you see, bears a time dependence. Okay, it has inherited a time dependence. So this means that this is the spectrum at whatever time you want to specify it in the universe, but this particular gravitational wave energy density parameter, we are interested in it today. Okay, so eta 0 is the conformal time today. Okay, because we want to measure the signal today, and it is while the gravitational wave energy density has been generated from a source in the early universe at the time eta star. Okay, and so using this kind of propagation, one takes the gravitational wave energy density power spectrum at time eta star, normalized to the energy density in the universe at that time, and then one redshifts it to today, okay, and divides by the critical density today. And you see that this particular formula gives something which is without dimensions. That's what you would like to obtain. Now, this is now still, so I want to make a connection with the detection process, okay, because this quantity is still quite theoretical. Okay, and so we have seen that what we want to say is, what we want to consider is that a source that has now stopped operating because it operated in the early universe, so the waves are freely propagating. We already said that. And also, what is important to consider is that over the time of the measurement done by the detector, the expansion of the universe is negligible. So this particular redshifting as 1 over a to the fourth, we need to apply it to understand what is the energy density of the signal today, but during the measurement, the stochastic background is stationary. Okay, so it does not depend on time because of the expansion of the universe, because the measurement is very short with respect to the lifetime, with respect to the Hubble time today, which is the characteristic time scale of evolution of the universe today. Okay, under this particular condition, one can then Fourier transform in time as well. So before it was not possible, as I told you already, in the Friedman universe, when one considers processes that take place like sources of gravitational waves or any kind of process in the Friedman universe, you cannot Fourier transform because there is in time. You cannot Fourier transform in time because there is no transitional invariance in time, while there is in space, and this is why we can perform a Fourier transform in space. Okay. But under this hypothesis that, okay, during the time of the measurement or even during the time of our lifetime, the universe is static, then one can perform a Fourier transform in time as well. Okay, and therefore one defines a frequency that is k over a naught over 2 pi. Okay, and in this particular, under this particular condition, it is possible to connect the definition that you can find in the literature about gravitational wave stochastic background detection, okay, which takes the point of view of the detectors, in which they always do a Fourier transform in time, and what we have been defining up to now. Okay, and in particular, here I am writing the power spectrum of the gravitational wave amplitude once we also Fourier transform in time. And these are the coefficients of the freely propagating basically plane waves, okay, for which now I fix the redshift to 1 over A0, and this is now can be connected with the power spectral density that is always defined in the literature of gravitational wave detection. And therefore one can write down then this relation, okay, that there is a bit of a computation to do to connect the two things that you can actually exercise yourself. This relation between omega, as I defined it here, but Fourier transformed in time, and the power spectral density, which is the quantity with which detectors are always dealing with. Okay, and now let's see, if we can say something very general as well with respect to, again, what is going to be the characteristic frequency of the gravitational wave signal. So I already showed you in the lecture yesterday that if we have a source of gravitational waves that is typically correlated on a scale L star, then this scale must be smaller than the Hubble scale at the moment of generation of the gravitational waves, okay, by causality. Now, if pretty obviously we associate a frequency of the gravitational wave signal that is going to be more or less, here there should be almost equal of the order of 1 over the characteristic scale of the source. Okay, this is simply an order of magnitude estimate. And therefore, the characteristic frequency of the signal must be larger or equal than the Hubble parameter at the moment of generation. Okay. So one can define now a parameter epsilon, okay, which is the ratio of the typical length scale of the gravitational wave sourcing process, so the size of the anisotropic stress, and the Hubble scale at the generation time, okay. And then this parameter epsilon, of course, enters in the relation between F star and H star. And here it how it goes, okay? If I want to write what I expect for the characteristic frequency of the gravitational wave signal today, well, this is just F star redshifted, okay, and therefore I can, so this particular parameter depends on the Hubble scale, of course, at the moment of generation, and therefore I can write this relation, okay, which is a one-to-one correspondence depending, of course, on the parameter epsilon between the characteristic frequency of the gravitational waves today and the energy scale in the early universe at which the gravitational wave sourcing process is operating. Okay, and this particular energy scale, I write it as T star. So this equation has been written, you can try to derive it from this by redshifting and inserting epsilon, okay. This has been derived under the assumption that the source of the gravitational waves takes place during the radiation-dominated era, and that is why there is this, it is linear in T, okay? T being the temperature, the ambient temperature of the universe at the moment in which the gravitational waves are being produced. Okay, so this is an extremely important relation, even though it is a qualitative one, okay, because we started from by saying, okay, the frequency of the gravitational waves is of the order of the inverse length scale, typical length scale of the source process, but this is a quite, I mean, a reasonable assumption. You know, but this equation is important. Why? Because I can use it now to plot this particular plot here, where in the y-axis I have f being the characteristic frequency of the gravitational wave signal today, and on the x-axis I have t star, so the energy scale in the early universe where the source is operating, and this black curve is indeed this relation extended to the transition between radiation and matter. So it's not exactly what I have here in this plot, is not exactly this relation. You see it is linear for the most part of it, but then when matter kicks in, it gets changes behavior, okay? So if you are a bit braver, you can also try to derive it, you know, putting the entire history of the universe in the Hubble factor, and you'll get this black line here. And now, of course, we have that today each gravitational wave observatory, be it Earth-based, like LIGO Virgo Cagra, or future space-based observatory like LISA or pulsar timing arrays, each observatory has its own sensitivity in frequency or frequency interval in which it can detect. We will see this in a bit more detail in a moment, but typically LVK, so LIGO Virgo Cagra, they detect around 100 Hertz. LISA detects around a millihertz, and pulsar timing arrays detect around the nanohertz. And using this particular relation here, you see an interval in frequency can be put in correspondence with an interval in the energy scale in the early universe where the process operating, generating gravitational waves is operating. And you see that this particular frequency ranges corresponds to very interesting energy scales in the early universe because they are much higher than what can be probed with the cosmic background and by Big Bang nucleosynthesis. Okay, so Big Bang nucleosynthesis occurs at 0.1 MeV, so it is down here. The cosmic background probes the universe at reionization, okay, of course also at inflation, but for here we are concerned about the fact that it gives a snapshot of the universe at the moment of, what did I say, reionization, I mean recombination, sorry, recombination. So it is down here at the electron volt. But gravitational wave detectors, at least in principle, allow to probe energy scales in the universe that are much higher than that. So they open up the space of observations to the very early universe. For example, pulsar timing arrays that operate around the nanohertz correspond, if I fix this parameter epsilon to 1, to the QCD scale in the early universe, where we expect the QCD phase transition to take place. LISA, with its sensitivity at the millihertz, okay, taking a bit smaller anisotropic stresses for the source, which is something quite reasonable, would correspond to the electroweak scale in the early universe, so 100 GeV. And LIGO Virgo Cagra that operate around 100 Hz would correspond to the Peche-Quinn scale at 10 to the 9 GeV, around 10 to the 9 GeV. So you see that all these detectors offer the opportunity to probe interesting energy scales in the early universe where we do expect important processes to have taken place, like phase transitions, the QCD, the electroweak one, and the Pechi-Quinn one. So in this sense, this is the interest really of gravitational waves as a way to probe the early universe is not just a theoretical interest, the fact that they propagate freely, what I was saying in the beginning of the first lecture, that they propagate freely and so they can bring direct information about the early universe. But there is another piece of information here that is added to that, which is the fact that our devices to measure gravitational waves today, by complete serendipity, actually have frequency ranges that corresponds to interesting epochs in the early universe. Okay, so it's not just theoretically that in principle we can access the early universe, it is also really our detector have the potential to access interesting phenomena in the early universe. Now, this argument has only been done based on the frequency interval of detection, but of course one needs also to have a signal with the correct amplitude, with a high enough amplitude, and if this is the case, we will see it in the future. Okay, and so there is this particular figure in which I want again to say the same thing, is the discovery potential of primordial gravitational wave background detection, right? So here, if you imagine that you have this axis in which time is going in this way, in the history of the universe, and energy is increasing in this way. So we go from the electroweak energy at which we have the recombination and the generation of the CMB to the MeV energy scale at which we have the neutrino decoupling and Big Bang nucleosynthesis and the formation of light elements. With the CMB anisotropies, we can access inflation, okay, which occurred, as far as we know, at an energy scale that must be smaller than 10 to the 16 GeV, okay? But gravitational waves, as I said, demonstrated in the very first lecture, they are decoupled since the Planck scale. And therefore, they propagate freely through the universe and they can bring direct information between, on this energy scale, on all these range of energy scale between inflation and Big Bang nucleosynthesis that we cannot access with electromagnetic emission. Okay, so we have up to now, no direct probe of these energy scales that, okay, can be very wide. If inflation occurs at low energy scale, this is still allowed, we don't know, then of course this range can be shorter, but if inflation occurs around the 10 to the 16, so at the gut scale, then you see that there can be a wide range of scales to which we have no access with electromagnetic radiation, but that we can access with gravitational wave detectors. And we expect interesting phenomena to have occurred in this range of scale in the early universe, like reheating after inflation, baryogenesis, phase transitions, dark matter, the coupling of dark matter candidates, etc. So this is really important to keep in mind. Okay, now I will go on with specifying a bit more the detectors and what is already known or will be known about the stochastic gravitational wave background. So we have already many upper bounds and in particular a possible measurement. Okay, so now we will see all that. Starting from this plot, in which here I have the gravitational wave energy density parameter today. So what has been defined in this particular equation here. So it's really the fractional energy density that is in gravitational waves today from whatever generation process, an unspecified generation process, as a function of frequency today. You see many colored curve here. We'll go through all of them, starting with these upper ones. These are, you see, sort of straight lines here, and what they mean is simply the fact that there cannot be too much energy in gravitational waves in the universe, because otherwise we would have realized that. And we would have realized that through Big Bang nucleosynthesis and the CMB. So if there was too much energy density in the gravitational waves in the universe, you would have spoiled these two processes that we measure with extreme precision. So how does it go? These particular bounds, gravitational waves contribute to the energy density in the universe, okay, of course, and change their background evolution. So here I wrote down Friedman equation as a Hubble scale squared as a function of temperature or time. It is equivalent. Here, this is in the radiation era. And of course, on the right-hand side, you want to write down the sum of all the components in the universe. And so here you have matter, standard matter, dark matter, photons, neutrinos, but you also have gravitational waves. Now, Big Bang nucleosynthesis, of course, predict the abundance of light elements, okay, and these abundances are measured today, and they are in extremely good agreement with the Big Bang nucleosynthesis predictions, I mean, for most of them. The process depends back then on the relative abundance of neutrons and protons, okay? And the relative abundance of neutrons and protons, because how many neutrons and protons you have determines how many light elements you can produce, particularly how many neutrons you have available. And of course, how many neutrons you have there depends on the freeze out of the weak interaction. And when the weak interaction freezes out, depends, after which you have the decay, okay, of the neutron, depend, of course, on the Hubble scale. Okay, so you have to balance the rate of the weak interaction with the Hubble scale. And you find, of course, that this occurs at around the MeV. But if you have an extra form of energy, this changes the Hubble scale, and therefore it will change the abundance of neutrons that you have, and therefore it will change the abundance of the elements. And this is how Big Bang nucleosynthesis sets an upper bound on the energy density that is allowed in gravitational waves. And this is this upper bound here, of the order of 10 to the minus 6. Cosmic microwave background is pretty much the same thing, okay? Because, of course, this is the freeze out of the interaction that gives a proton plus electrons gives an hydrogen atom plus a photon, so it is exactly the same thing. Instead of having the weak interaction, you have this scattering for the freeze out of this scattering for the cosmic microwave background, and therefore exactly the same argument goes through, just at a smaller temperature, okay, at a smaller energy scale of the order of 0.3 electron volt. Okay, and therefore, so in this case as well, you cannot have too much gravitational waves around in the universe at this particular epoch, otherwise you would spoil recombination. And this is this other bound. So here they extend, they extend, you see the Big Bang nucleosynthesis bound stops here. This is the horizon, the frequency that corresponds to the horizon at Big Bang nucleosynthesis. Of course, this is the reason for this is that the bound does not constrain the presence of gravitational waves after Big Bang nucleosynthesis has taken place. So it stops here. Okay, so everything that happened at later times, so smaller frequencies, is not constrained. CMB, though, goes a bit further down because it occurs, recombination occurs later in the universe, in the history of the universe. And therefore, here you have the horizon, the frequency corresponding to the horizon scale at recombination. Okay, another thing that is worth noticing is that these bounds are on the integrated gravitational wave energy density. Okay, so here I plot them as horizontal lines, but in reality it would be a bound on an integral. Okay, so it's difficult to plot it as a function of frequency, and that's why it's just a straight line. Okay, we can go on now with bounds, observational bounds from CMB probes. Okay, so these are low frequency bound from CMB anisotropies and polarizations. This bound has been settled by Planck, BICEP, WMAP, all the detectors of the cosmological background, and here you see the potential improvement by light bird. Okay, so what am I talking about here? This is the integrated Sachs-Wolf effect, okay, that the presence of a tensor fluctuation or gravitational waves um, causes okay, so the presence of a gravitational wave generates a temperature anisotropy in the CMB temperature by integrated Sachs-Wolf effect, meaning that this effect occurs from the time of the coupling up to today. Okay, so it is an integrated effect. It is a temperature fluctuation due to an integrated effect over the tensor modes. Okay, and one can, by assuming some form of a power spectrum for the tensor mode, okay, that here I just write down as an amplitude times dependent on k, I just made it dimensionless with some spectral index that I called NT. Okay, so for now this is absolutely free, okay, just parameters. One can then calculate what would be the CMB spectrum, the CMB anisotropy spectrum here in temperature due to this particular bound. And then, because you do measure this CMB temperature spectrum, as you all know, you can bound the parameters. It's very, very, very simple. A bit more involved, but conceptually not different, is the fact that, as you know, CMB photons are also polarized. Okay, and one can decompose this polarized field into two polarization patterns, the E mode and the B mode. And here in particular, the tensor component, so the gravitational waves, generate only B mode perturbations. No, sorry, it's not true. They generate both patterns, but is a scalar perturbation do not generate the B mode. So the B mode is a direct access to the presence of tensor perturbations in the early universe, okay, or at the moment of CMB. And therefore the B mode has been also measured by Planck and BICEP, and therefore one can use this measure to infer a bound on the presence of a tensor anisotropy. Okay, so using both the temperature and the polarization measurement, one can put an upper bound on the tensor, on the gravitational waves in the universe at the moment of recombination. So this particular range of the frequency range over which this bound is relevant goes from the Hubble, the frequency corresponding to the Hubble scale today to the frequency corresponding to the Hubble scale at recombination. This is because it is an integrated Sachs-Wolf effect, okay? If you want to see it, say it more in a simpler way, it is because the CMB probes the universe at recombination. Okay, and this is what are the measurements. This is the CMB spectrum as a function of multiple. That's the temperature in which no tensor component has been observed, the E polarization and the B polarization, on which as well there is no tensor component that has been observed. So I would like to stress that these bounds apply to any form of gravitational waves that is there before recombination, but usually you are used to see them applied to the gravitational waves arising from inflation. Okay, because indeed these are bounds at very large scales, and so it is difficult to find other processes that would produce a gravitational wave background at these huge scales corresponding to about the horizon at recombination and larger. Okay, so that inflation does, because inflation produces a spectrum that is scale invariant at all scales. So that's why these bounds are always, you are used to see them applied on the so-called tensor to scalar ratio that is defined in the case of gravitational waves generated by inflation. And what I'm sure, so this would be prediction of signals from inflation, and this is instead the lensing, and these in particular these points here, the violet and the blue, are the measurement by Planck and bicep. Okay, so these are the upper bounds. And this is also, I think, how you are used to see this particular upper bound on the, as I said, on what is this parameter, which is the tensor to scalar ratio. So it is the amount of gravitational waves or tensor modes one has with respect to the scalar component that has been measured, that generates this signal. Okay, and these are the bounds on the amount of tensor that are put by different combination of CMB data confronted with the prediction of these different inflationary measurement. And this is how the projected sensitivity on this particular parameter are with the future detectors. And this is light bear that I also had on that plot, which aims at a bound on the tensor to scalar ratio smaller than 10 to the -3. So there is improvement expected in the next, let's say, 20 years on this particular, or 10 years on this particular parameter. Okay, and now, so these two bounds, if you want, are a bit sort of indirect that I just described, because CMB and BBN are on the integrated energy density and of the gravitational waves, and Planck, light bear, they are on the CMB, come from the measurement of the CMB. Right, but now let's see direct detectors of gravitational waves, what they could do. Okay, so present and future gravitational wave observatory. And let's start with Earth-based one that are operative now, LIGO, Virgo, and CAGRA. And these, as I said, they operate around 100 Hertz, and their sensitivity corresponds to these green curves here. I have the observation run 1, 2, and 5 of the LIGO Virgo Kagra network. Okay, that's their sensitivity. So 1 and 2, they already did it, 5 not yet. And here is what one expects by third generation Earth-based gravitational wave detectors like Einstein Telescope and Cosmic Explorer. These are the projects, the future projects respectively in Europe and United States. Okay, so here you have a picture of one of the two LIGO, and you see these are interferometric devices with arm length of 4 kilometers with this particular frequency range of detector. In the future, we will see new detectors with much higher arm length and that can go consequently at lower frequency. And they have, in general, factor 20 improvement on the sensitivity. Okay, and what are the detection targets of these instruments? As you all know, because they already did it, black hole coalescing binaries of masses of few to 100 solar masses, but also neutron star and neutron star black hole binaries that they also have already been observed. Supernova explosions, not yet. They probably will be observed in the third generation detectors, and also stochastic gravitational wave background if it is there. This is what the detector have done up to now in the context of individually resolved black hole binaries, neutron star binaries, and neutron star black hole binaries. Okay, they have a lot of detection, about 90 binary mergers detected. Okay, as I'm sure you are all aware. On the other hand, there is no measurement of the stochastic background for now, but only upper bounds. And actually, there is no expectance that there will be a measurement of a primordial stochastic background, if it is there, by Largo, Virgo, and Kagra, not even at their design sensitivity, so really what they will reach as the best sensitivity ever in a time scale of maybe 10 years. It is not expected that they will detect a background from the early universe. Why? Because it will be covered by the foreground that you see here, the prediction by binary neutron star and binary black holes. Okay, so at the level of a stochastic signal, what we expect is that at their design sensitivity, Earth-based detector will actually observe this particular confusion noise from the superposition of all the black hole merging black hole binaries and neutron star binaries in the universe. Okay, so but for now, not even this foreground has been detected. There are only upper bounds, and here you see how the upper bounds have been put. They assume this kind of form for the gravitational wave density parameter, so a power law in frequency with a given amplitude, and they put an upper bound on the amplitude and a very, of course, lousy upper bound on the power law because the amplitude is not detected. So. Okay, and how they perform this measurement is that they use cross-correlation of signals from different detectors. Okay, because these are instruments that are noise dominated, which means that they basically always observe noise. From time to time, there is the merger of a black hole binary that comes up from the noise, and they pick it up. But the way they pick it up is always to cross-correlate the signal, the data output of different detectors, assuming that the noise is independent. And therefore, with the cross correlation, the noise goes away and the signal remains. And this is exactly how they also plan to detect a stochastic background and to distinguish it from the instrument noise. Okay, they assume that because these detectors, there are two in the United States, widely separated, one in Japan, one in Italy, and therefore they say, okay, the noise of each of them is uncorrelated with the one of the other interferometers, while the signal is correlated because it comes from outer space. Okay, and so that's how the measurement is performed. Okay, so that's the situation for Earth-based interferometers. Now let's go to LISA, which is a future space-based interferometer. Okay, here obviously the interest in going to space is that there is no seismic noise, which is what actually bounds the lower frequency here of accessibility on Earth. Okay, but in space there is no signal noise, and also one can afford to go to much longer arms. And therefore access a completely different range in frequencies, which is around the millihertz, so from 10 to the 4 to about 1 millihertz. So LISA is a project that is now has now been approved and is under construction. It will fly in about 2035, and it is a triangular constellation of three spacecraft. Each spacecraft contains two masses in free fall, and the spacecraft are connected by lasers that perform the interferometric measurement, so measure the distance between the masses in free fall. And the arm will be of 2.5 million kilometers, which means for a gravitational wave signal of about 10 to the minus 21, okay, which is the typical amplitude of a black hole binary merger, that this device will be able to measure picometer displacement of the masses. Okay, so this particular observatory, then as I said, we will have it in the sky in about 10 years. It takes 2 years to go to orbit, so we'll have, if everything goes well, the first data in the second half of the 2030s. What are the detection targets? Detection targets of LISA is an extremely rich category of sources. And here you see, so the amplitude, the strain amplitude spectral density of the interferometer in blue, as well as the one of predicted sources as a function of frequency. I say predictive sources because we should not forget that this is a completely new range of frequency. So we have predictions of what is up there, but we are not completely sure. And in particular, the highest signal to noise sources will be these straight lines here that represent the in-spiral and merger of massive black hole binaries, so binaries of black holes that reside at the center of galaxies. So these are completely different than those that are measured today by interferometer, Earth-based interferometer. So these are binaries that go from a few to about 100 solar masses. Here we talk about binaries that go from 10 to the 4 to 10 to the 7 solar masses. So really different category of black holes. But LISA, we also measure the galaxy. So I think there was a question yesterday about this. So this would be all the binaries that we expect that are present in the galaxy in the spiral phase. So these are, for example, white dwarfs binaries, neutron star binaries, black hole binaries. And these red dots here are the actually the binary pulsars that we know are there because we measure them in the electromagnetic emission. Okay, so these we know that when we turn on LISA, we will have to see the gravitational wave emission by these binaries. And these are all the ones that we expect will be resolved. It's about 20,000, but there is also a confusion noise here generated from all the binaries in the galaxy that are not that have signal to noise ratio too low to be individually detected by LISA. And you see this is plotted here as an extra source of noise over the sensitivity of the instrument. Okay, other kind of sources interesting are these traits here. They are stellar mass black hole binaries. So these are the sources that are regularly now detected at Earth-based interferometers. LISA can pick them up at lower frequency and therefore earlier in the spiral phase. LIGO Virgo Cagra sees the merger of this object, while LISA sees the same kind, the same category of objects, of black holes, but while the binary is far into the end spiral. And there will be a handful of sources given by, so the predictions are that a handful of sources will actually be picked up by LISA late enough in the spiral phase so that these particular binaries will merge afterwards a few years later, from 5 to 10, 20 years later, in the Earth-based band. So there is a possibility of having a multi-band detection, of seeing something with LISA, a binary in, in the sky, a black hole binary in the sky of 50 solar mass, let's say, in the spiral phase, and LISA will see will say, okay, so the parameter of these binaries are such that it will merge in 15 years with the precision of 1 hour in the LIGO Virgo Cagra band. And then LIGO Virgo Cagra or third generation experiments, if they will be there, will be able to pick up then the same binary at when it merges. Okay, and the last category of sources that LISA will possibly detect are extreme mass ratio in spirals. These are objects composed of a very massive black hole at the center of a galaxy, so an object of 10 to the 4 to 10 to the 7 solar mass. And around it, there is a compact object, for example, another black hole with a much smaller mass of the order of, say, of 10 to 100 solar masses. And this small black hole is captured in the space-time potential, in the potential of the big object, and it's actually plunging into the big black hole. And this the orbit of the small object, as it loses energy and approaches the central black hole, emits there is a gravitational wave emission that is associated to this, and it is in the millihertz band. It is expected to be in the millihertz band, so it is a target for LISA. Okay, so this was a general description of the instrument, but let's see now focus again on stochastic gravitational wave background. So what LISA will see, or we expect that it will see or detect in stochastic gravitational wave background. Well, first of all, the confusion noise from binaries in the galaxy. Okay, this is what I showed you already here, mainly white dwarf binaries. There is going to be also a confusion noise from extragalactic binaries, okay, both white dwarfs and black hole binaries, that is going to be pretty high. And here you see it, so this is the same plot as here, but plotted in terms of the gravitational wave energy density parameter as a function of frequency, sorry. And this blue line here is indeed the stochastic foreground we expect from the superposition of all stellar origin black hole binaries, so the same objects here, stellar origin black hole binaries that cannot be individually detected because they have too low signal to noise ratio, okay, as I was saying maybe yesterday. Okay, so this is the signal as we expected. This is the background from the galaxy. Okay, these dashed lines are the noise of the instrument, so the sensitivity of the instrument. So this particular line corresponds to the light blue one here, is the instrument sensitivity, and this is the sensitivity to stochastic backgrounds. Okay, so what is important to notice is that one cannot really assess the sensitivity to a stochastic background just with respect to the instantaneous sensitivity of the instrument, because stochastic backgrounds are stationary signal, so the more you observe them, the better you observe them. Okay, and this is it is taken into account by constructing what is called the power law sensitivity of the instrument. You can have a look at that in a paper. Sorry, I don't have the reference here, but a paper by Train and Romano, in which they propose this particular graphical way to transform the sensitivity of the instrument in order to assess really what is the sensitivity in particular to stochastic backgrounds. Okay, so now you know what is this curve, you know what is this curve, you know what is this, you know what is this, and what about the rest? So the rest are predictions of possible signals from the early universe that fall in the LISA frequency band. We have here a signal from possible signal from cosmic strings. This is from second order scalar fluctuations from inflation, and this is from a phase transition. So if it doesn't say much now, we will see what these signals are. Okay, but here this picture is just to tell you that okay, not only we will have the foregrounds from the astrophysical sources that are sure. On top of that, the fact is that there are many possible signals from the early universe, and they have very different frequency shape. And so it is extremely challenging to be able to detect something with LISA and claim that it is a signal from the early universe from a particular source. Okay, it's going to be a real challenge. Of course, the challenge will be easy if the signal has a very high signal to noise ratio. But if the signal is, at the limit of the sensitivity range, then it's going to be extremely difficult. Why so? Because in particular, with LISA, there is only one device that measures, and so we cannot perform this cross correlation as it's done with Earth-based interferometers. And therefore, this means that there is no way to distinguish a stochastic background from the instrument noise. Okay, so we will only be able to detect, to claim with reasonable certainty detection if the signal is very different from the predicted instrument noise and with very high signal to noise ratio. Okay, so far for LISA. And now maybe I can take questions before I go to pulsar timing arrays, if there is any question.
Okay. The floor is open for questions now. If you have any questions, please ask. Yeah, I had a question from quite early slide, like when you define the power spectrum, A K power L with power spectral index. Yeah, so much earlier, like when you define, yeah, this one. So I'm asking, yeah, when we take in cosmology, we typically take the Zeldovich approximation, like Harrison Zeldovich as NTS1. So I'm just asking here, there is any, like, how should I say, scale invariance needed or anything like that? So is there a phenomenological bound on the ND, just like Harrison Zeldovich, we take the NT to be 1? So yeah.
Absolutely. So yes, so here I've written it in full generality, because in reality, to place a bound from the cosmic background observation, you don't need to assume an Harrison-Zeldovich spectrum. Okay, so you can put a bound on the tensor component with a free spectral index. So that's why here I put it in all generality. Now, The measurement of the scalar component tells you that the scalar component has a Harrison-Zeldovich spectrum. You explain it in terms of inflation, okay? And in the context of slow roll inflation, then you also can predict the gravitational wave signal, okay, or the tensor signal, and you see that then this particular spectral index here in slow roll inflation is related to the derivative of the potential, you know, to this epsilon parameter, which is the derivative of potential divided by the potential itself, and therefore it is small. So this is about zero. Okay, but the fact that this is about zero is a prediction. It's only true if we are considering here a gravitational wave signal coming from slow roll inflation. But in all generality, if you want to put a bound, you can also assume a bound that is disconnected from any model. You can also assume a power spectrum which is completely generic. So this was the philosophy here. That's why I didn't set NT to 0.
So I'm
Does
just
it
asking
answer
that.
the question?
Yes, yes, absolutely. So I just have a slight comment that in the Zeldovich approximation, the advantage is that it becomes scale invariant, right? So after the super horizon entry, those freezes, so we can see it in the CMB. So here, if you take n to be very small, like the first Laurel parameter, I guess epsilon one you are fixing. So doesn't it mean that those B modes, etc., like the tensor perturbation signatures would be very suppressed when
No,
it re-enters the
so
motor? Yeah.
here you see what is the prediction in the context of slow roll inflation.
Okay.
Okay, so as you say, it is scale invariant. Of course, here it is modulated by the transfer function, but it doesn't mean that it is small. Okay, so
Okay.
the NT is 0, but there is the amplitude. And the amplitude here is rewritten in this case in the tensor to scalar ratio.
I see. And
Okay.
yeah, sure. And just for second question, because you have put it the Storovinsky inflation also like R squared. So for
Yeah, so
Storovinsky
this I
inflation,
didn't do. I take this figure from
okay.
this paper.
So for Storovinsky inflation like FR gravity, how does the NS compare? I mean, you take the Jordan frame and get the potential to constrain it. I mean, in the FR gravity, how it NS constrain?
No,
In inflation, you already told that it is the first Laurel parameter that would detect, but in the
yes,
Storovinsky potential, how it did? Yeah.
so in R2 inflation or Starobinsky inflation, it is also scale invariant. You see, it's exactly the same spectrum. It's just the amplitude that is lower.
Thank you very
Okay,
much.
so this NT is the prediction is that this NT is also 0 or close to 0, let's say.
Okay. Other questions? It seems there are no other questions.
Okay. Okay, so now we will focus a bit more on pulsar timing arrays that are important because they have most likely performed the first ever detection of a stochastic gravitational wave background. Okay, so what are pulsar timing arrays? There are several collaborations, the Chinese one, European one, Nanograv is the American one, Parkes pulsar timing array is the Australian one, and that in some cases put their data together to lead to the international pulsar timing array. And these are collaborations that use the data from radio telescopes. And these radio telescopes measure the radio emission from pulsars, which are rotating neutron stars that have a beam that emit a beam of radio electromagnetic emission. Okay, and rotate. And therefore, regularly, depending on the rotation, this beam of radio emission arrives to Earth. These objects have a huge moment of inertia. They are extremely stable in their rotation, and therefore these pulses, these radio pulses, arrive to Earth at extremely regular time intervals. Okay, and so they can be used as clocks in the sky, in the sense that they provide a measurement of time at extremely precise intervals. These objects, therefore, have been used to perform many tests, for example, test of general relativity. And they can also be used to measure gravitational waves. Why? Because these very precise arrival times can be altered by the presence of a gravitational wave passing between the pulsar and the Earth. Okay, so the fact that space-time is deformed between the pulsar and the Earth will induce shifts in the time interval of these of these pulses. Okay. Naturally, there are many sources of noise in this measurement. That are due, for example, to the atmosphere, to the fact of relating what is the time at the pulsar and the time at the Earth. So the thing is that one needs a network of pulsars to perform the measurement, okay? Because the network, once again, as it is true for for LIGO Virgo Cagra, allows to compare the measurement in different, coming from different pulsars that have independent noise. Of course, not the atmosphere noise, but the one due to the pulsar rotation, instability, or these kind of things. Okay, so these are networks. So the radio telescope observe many pulsars, take the timing of many pulsars, and the observers construct what is called a timing model. Okay, so they given the atmospheric disturbances, given the characteristic rotation of each pulsar, etc., they build a prediction for what is the cadence of the pulses that are emitted. And this prediction, okay, is then compared to the observation to infer what are called the timing residuals. The timing residuals are at every pulse how much it deviates from the model. Okay, and these timing residuals is exactly where the gravitational wave effect is looked for, because it would be an effect due to the deformation of the space-time that is not accounted for in the timing model. Okay. So this is how the measurement is performed. What kind of gravitational wave can these pulsars pick up? So as I told you, they have a frequency around the nanohertz. And this is due to the time span over which the pulsar nectar has been observed. Okay, so it is of the order, let's say, of a 10-year. Which gives you more or less the nanohertz. And therefore one needs to find gravitational waves of the same sort of frequency. And turns out that these can be, gravitational waves of this very low frequency can be emitted by inspiraling supermassive black hole binaries at the center of galaxies. Now, these are binary, black hole binaries at the center of galaxies, but not of the same kind of those observed by LISA, because LISA can pick up masses up to around 10 to the 7 solar masses. Here we talk about 10 to the 9 solar masses. And this makes sense because these frequencies are much lower, you see, so we need a more massive object. Okay, so that's the detection target. And now we can see a bit what is the principle of the measurement. Okay, because it is sometimes referred to wrongly in the literature. So that's why I think it is useful to understand what is going on in a bit more detail. So you can actually, because sometimes the literature is confusing. Okay. So what we access here is the gravitational redshift caused by gravitational waves emitted by a faraway source, okay, here, traveling through space-time, okay, between the pulsar and the Earth. So we have a source, a supermassive black hole binary. It is emitting gravitational waves, and these gravitational waves are, spherical waves that go about in the entire universe, and in particular, they are present on the path between the pulsar and the Earth. Okay, so at a given emission time, the pulsar emits a radio beam, a radio pulse, okay, electromagnetic radio pulse, and this travels through space-time, and it is received at Earth at an arrival time. Okay, and of course, there is here on this path the effect of the gravitational waves. So the photon from the pulsar, so if you write down the metric line element, is of course 0. The S squared for a photon is 0. And so the dt is equal to plus or minus the square root of the metric between the pulsar and the Earth, perturbed by Hij, the gravitational wave measurement. Okay, and this is the usual gravitational redshift. Okay, so the time interval which you get from integrating this equation in time gives you the distance L between the pulsar and the Earth in Minkowski spacetime or Euclidean spacetime, which is this delta Ij, okay, plus a perturbation, which takes this form. It is, of course, the so ui, uj, u is the vector from the pulsar to the Earth, and then you have the integral from the pulsar position to the Earth along the path of course, Hij. Hij that starts at time t, so Hij, the metric perturbation, okay, that you take at reference time te, now plus s, where s is the integration variable, and a position re, which is the position of the pulsar, plus su. Okay, su is the path integral, s is the variable of the path from pulsar to the Earth. Okay, so this is the effect of the metric perturbation on a single beam, on a single emission of the pulsar. And this is what is called the gravitational redshift. Okay, of course, this quantity here is not measurable, right? Because unless you know the reference quantity. So unless you know L and you know TE, of course you cannot really measure. So I mean, you measure the time of arrival. Sorry, it's contrary. You measure the time of arrival, okay, but you cannot measure Hij unless you know the time of emission, which is something that you actually don't know. Okay, so the principle of the measurement is not the gravitational redshift, as you might read in some of the literature, but it is the fact that you compare two nearby in time pulses, okay? So you need to compare the first pulse with the next one, okay, to be able to measure something. Now, the next pulse, of course, is emitted at time te plus p, and arrives at the time which is te plus p plus some time shift. And the time shift again depends on the path and therefore on the perturbed metric. And now, so what you obtain for delta t is pretty much the same here. Obviously, the static part, so the part that comes from delta ij now goes away because you are comparing two pulses and this part is the same. Okay, when you subtract here, you want the delta t. So this part goes away, but the part that depends on the path now takes the gravitational wave, right? The gravitational waves at time te plus p, okay, when it was emitted for the second pulse, of course, integrated over the path at the same position as before, the position didn't change, minus, minus is delta t, the gravitational waves at the of this pulse before, okay, at te plus s. And now, of course, here you see that this effect is present only because the gravitational waves is time dependent, okay? If we had to compare, if we were in a condition in which the metric perturbation is due to the presence of a black hole, for example, or whatever mass density that is static, clearly this goes away, okay? Because you subtract something that does not depend on time. On the other hand, the gravitational wave is time dependent, and that's why there is an effect on this. So the time of arrival, is not the difference between the time of arrival is not the same as the one at emission, but there is a shift. Okay, and now here basically it is just a change of variable that you can do. I mean, you can exercise, right? You call this big X everything here, fixing as well that the direction of propagation of the wave is k that you put in this reference system as this RS, okay? And therefore here you have transformed your integral in S as an integral in the X, okay, from different boundaries, and it gets out this particular factor here, 1 minus k dot u. Okay, and here it simplifies, so here you really see that this is Hij taken at this variable x plus p, okay, which is the difference in the emission time. So this is just rewriting of the integral. And now you want to see, okay, now I have the effect. Where does it come from? Where can it come from? Okay, and so you say, well, let's suppose that the source is an spiral of a supermassive black hole binary. Okay, what would be the typical scale of the time variation of the metric perturbation due to a supermassive, due to the gravitational waves emitted by a supermassive black hole binary? Okay, so you take this relation here, This is basically comes really from Kepler law. So you consider that this binary, is described by Newtonian gravity. Of course, you can go further, but in GR they describe it in post-Newtonian expansion, but there is no need for this order of magnitude estimate of the effect. And in this context, in the context of Newtonian gravity, there is a simple relation between the frequency of the gravitational waves that are emitted by the supermassive black hole binary or by whatever binary, and tau, which is the time to coalescence. Okay, so that means how much time will pass before this source is going to merge, before the two black holes are going to merge. Okay, so it's a time interval and it's the time to coalescence. And it is an inverse relation and depends on the chirp mass of the source. The chirp mass is a particular combination of the masses of the two black holes, okay, which is useful because it always appears into this kind of equations for the gravitational wave emission, and so instead of every time writing m1 m2 over m1 plus m2 to the 3 5 or 1 5, one just writes the chirp mass and it is easier. So, and it is then inversely, the frequency is inversely proportional to the chirp mass as well. Okay, so here you see that if the two objects have the same mass, of course, this relation simplifies and the chirp mass is equal to the mass. Okay, and now what you see is that basically if you put two black holes of chirp mass of the order of 10 to the 9 solar masses here, and that have a time to coalescence of the order of 10 to the 4 years, so they are very far from coalescence, then you fall into the frequency of around a nanohertz. Okay, so I see now that it is almost midday, so maybe even if it is a bit stopping in the middle, we can maybe stop here, and I will go on tomorrow with the analysis of the typical delta T. And I can take questions if there are.
Are there any questions? Okay, though there are no other questions, so let's thanks Chiara for the wonderful lecture.
Okay. So sorry for stopping in the middle, but I mean it's now time. So, but I think tomorrow I will do a short summary so that we go back to this part.
Yeah, sure.
Okay, thank you very much.
Okay, see you tomorrow in the
Bye.